All right, so now we're going to look at doing operations with complex numbers. It's an L. Complex non-real numbers in polar form. So we looked last class at how to do it when they're in rectangular form, like a plus bi. How do we multiply, add, divide? Now we're going to look at operations when they're in polar form. So let's take two complex numbers. We'll call z sub 1 our first complex number in polar form, complex non-real. And we know that it's in the form r sub 1 of cosine times cosine of theta sub 1 plus I times sine of theta sub 1. Whoops, I'm putting i's there. Okay, so that's our first complex number in general form. I'm trying to develop a formula. So we know that normally these will have numbers here, and a radius and an angle, but we're doing it in general. So we're going to keep track of these variables so we can make like a formula. Then we'll take our second complex number and do the same thing, and we'll just index all of these constants as sub 2. Should be in parentheses. All right, so we're going to now look to multiply these two numbers. So z1 times z2 is going to be equal to r sub 1 cosine theta sub 1 plus I sine theta sub 1 times r sub 2 cosine theta sub 2 plus I sine theta sub 2. All right, and then what we can do next is I see kind of like, I look at this as like 4 parts times each other, right? Because there's multiplication in between here and in between here. So it's going to be equal to r sub 1 times r sub 2. And then, because I can multiply those together, so I would do that when they're numbers. And then I'm going to have cosine of theta sub 1 plus I sine of theta sub 1 times cosine theta sub 2 plus I sine theta sub 2. All right, so now what we do is we look at multiplying these two parts together here, these two factors. And inside of there, I see 2 terms in each. Right, those are our terms. So we're going to kind of distribute, do FOIL, right? So we're going to multiply the first times the first and the first times the second. So I'm going to try to write a little smaller so I can fit it. So we got r1 times r2 times cosine of theta sub 1 times cosine of theta sub 2 plus I times cosine of theta sub 1 plus times times sine of theta sub 2. Should be putting these in parentheses. Now I'm going to distribute the sine of theta sub 1. So it's going to be the I, there's an I with it, I sine. So it's going to be I, and I'll write the cosine first. Cosine theta sub 2 times sine theta sub 1. Let me move this over, buy a little more room. And then I multiply that times that, and I get plus I squared sine theta sub 1 times sine theta sub 2. Okay, so now what we want to do is I see 1, 2, 3, 4 terms here. And 2 of them are imaginary and 2 of them are real. Remember, this one over here is real because of the I squared is really a -1. So I'm going to regroup these in pairs. I'm going to rewrite them. I'm going to write the reals together and then the imaginaries together. So I got this cosine theta sub 1 times cosine theta sub 2, and the other real part is going to be minus sine theta sub 1 times sine theta sub 2, and then it's going to be plus the imaginary parts. And we're going to factor out the I as well. So I times, now these are the two parts that have the I in them. So it's going to be cosine theta sub 1 sine theta sub 2 plus cosine theta sub 2 sine times sine theta sub 1. I had to kind of move it down there. All right, I had to squish it in at the end. All right, so now what we're going to look at is these guys should be reminding us of something. These look like our sum and difference formulas. Remember, like this could be possibly like the sum formula for cosine or the difference for cosine. Well, this one indeed is the sum for cosine. So I'm going to replace it with that. So R1 times R2 times, instead of all of this stuff here, I'm going to be able to write cosine of the first angle plus the second angle. That takes care of all of this. All right. And then plus I times, if I look at this one, again, this is another one of those sum or difference formulas that we had from earlier in the year. And that one's going to be the sum formula for sine. So it's theta sub 1 plus theta sub 2. Okay? So it simplifies down to that. And this would be our formula for multiplying complex numbers in polar form. Because we don't want to go through all these steps every time, so we sort of made a formula. And what we would say, if I were to say this in words, it's not that bad once we have a formula. We say when we're multiplying complex non-reals in polar form, we multiply the magnitudes, which that's the r's, and we add the arguments. Whoops. That's the thetas. So that's saying it in words. So let's do an example. Find the product of this complex number, 3 times cosine of 35 degrees plus I sine of 35 degrees, and this complex number will say 2 cosine 10 degrees plus I sine of 10 degrees. So we know our formula. So the answer of Z1 times Z2 is going to be to multiply the magnitudes, or the radii there. So 3 times 2, we get a 6. And then it's going to be cosine of the angles added together. So it's going to be 45 plus I sine of 45 degrees. All right. Whoops. And it's that easy. Now, that's if we leave it in polar form. And then we can also convert that pretty easily to rectangular form, if we like, with the conversion we did in class today. Or it depends when you're watching this. Could have been yesterday. But for now, we'll just leave it in polar form. If you did convert it, just for a little practice, this would be 3 root 2 plus 3i times root 2. That would be in rectangular form, the same number. All right, so I'm going to have you try one. So you're going to try to multiplying these two complex numbers in polar form. 2 cosine of 55 degrees plus I sine of 55 degrees. And the second one Let's do 5 cosine of 65 degrees plus I sine of 65 degrees. And you can leave your answer in polar form. You don't need to convert it to complex. To rectangular complex form. Leave it in polar, complex polar form. So pause the video and do that. Okay, welcome back. You should have gotten 10 times cosine of 120 degrees plus I times sine of 120 degrees. That should have been your answer in polar form. Now I do want you to convert this for a little extra practice. Convert this into rectangular form. So pause the video and see if you can do that. All right. So thank you. And you should have gotten -5 plus 5I times root 3. Same number in rectangular form. Now we're going to derive a formula for the dividing complex numbers in polar form. So again, we're gonna do this in general. So we have the formula. So we can take our first, complex number in polar form, all sub 1s. And now we're going to divide them. So if we divide these two numbers, z1 divided by z2, all right, so the first thing is, again, we can look at the multiplication here between these two things and sort of do that individually. So we can do r sub 1 divided by r sub 2. We could divide their magnitudes. Now just deal with the angles separately. Cosine theta sub 1 plus I sine theta sub 1 over cosine theta sub 2 plus I sine of theta sub 2. There we go. So, wait, I have too many parentheses there. All right, so how do we divide these from here? Well, we can't really do any division here with this stuff. Okay, because of the addition here, we can't actually divide anything. So what we're going to do is when we're in this position, what we've been doing lately is let's try to multiply the bottom by the conjugate, and then of course we have to multiply the top by the same thing and see if the middle terms, well, we know the middle terms will cancel out, and see where that gets us in the denominator. You're going to see something sort of nice happen here in the denominator, which kind of does our division for us. So whatever I multiply on the bottom, I also have to multiply by on the top. Right, so let's see what happens on the bottom. Something pretty neat. So again, we just kind of keep track of dividing those magnitudes there. Let's do the bottom first. So I get cosine squared of theta sub 2. And then I know the middle terms cancel out, so I'm just doing first times first and last times last. So I get minus I squared times sine squared of theta sub 2. Now on top, we know that I squared is going to turn into -1, right? Now on top, we also do the distributive property. So I get cosine of theta sub 1 times cosine of theta sub 2 minus I times cosine of theta sub 1 times sine of theta sub 2. So that part came from me distributing this first term here to both of those. Now I'm going to distribute the I sine theta. So I'm going to get plus I, and I put the cosines first, theta sub 2 sine sub 1. And then this last one here times the last one there. So then I go minus I squared. Yeah, hold on one second. Okay. minus I squared times sine theta sub 1 times sine of theta sub 2. Gotta extend this fraction bar a little bit here. Okay, so next up is we're going to regroup in the numerator the real parts with the imaginary parts. So z sub 1 over z sub 2. We're going to keep track of the division of those magnitudes. So I've got the real part, cosine theta sub 1 times cosine of theta sub 2. And the other real part is going to be this I squared, because it's going to turn to negative 1. So it'll turn this into an addition symbol. And then this stuff is going to get, so plus this will go with this part. So sine, right? So plus sine of theta sub 1, sine of theta sub 2. Now I'm going to do the imaginary parts here. So I've got minus I, or actually let's do it this way. Let's put the positive one first. We got plus I, and we're going to factor out that I. Cosine of theta sub 2 times sine of theta sub 1. So I put this term first and I factor out the I, and now I'm going to put this term next. Minus cosine theta sub 1 times sine of theta sub 2. Alright, so that's what happens in our numerator so far. And then of course, these are going to be our sum and difference identities again here. It will be one of those. On the bottom, this I squared here becomes negative 1, so it turns this into a plus. So on the bottom, I've got cosine squared theta sub 2 plus sine squared theta sub 2, which we know is 1. That's the neat thing that happens by multiplying by the conjugate on both the top and on the bottom. So that does a lot. That goes a long way towards our simplification. So now we keep track of our dividing our magnitudes. And this next piece here, the part that I highlighted, is a sum or difference formula. This is your difference formula for cosine. So it's going to be cosine of theta sub 1 minus theta sub 2. It's really important which one comes first here. Okay, so you got to have the order right because it's subtraction this time. Didn't matter before when it's addition. So theta sub 1, if we go all the way back and remember, it's the angle that's on top in the numerator has to come first. So that'll be easy to remember. And then plus I times sine of, this is this difference formula for sine, right? This part is sine of theta 1 minus theta 2. So that's going to be sine of theta sub 1 minus theta sub 2. And again, the order matters. All right, so that is our formula for dividing complex numbers. So we do it once with variables so that we don't have to do all these steps every time we try to divide these complex numbers. So if I were to write it in words, like I did last time, I'm not going to write out when dividing two complex numbers. I'm just going to say you divide the magnitudes and subtract the arguments. Remember, the magnitudes are the r's. Whoops, I'll say it this way, r1 over r2. And the arguments are the thetas, theta 1 minus theta 2. It's important to note that you got to do the numerator, the theta from the numerator minus the theta from the denominator. So don't forget to do that. So let's look at an example. Example number 2. Let's divide these two complex numbers. Z sub 1 is 6 cosine of 125 degrees plus I sine of 125 degrees. And then Z sub 2 is going to be 3 cosine of 65 degrees plus I sine of 65 degrees. So I want to divide, I'm going to go Z1 divided by Z2. That's going to be equal to 6 divided by 3 is 2 times cosine. Now I do the numerator, so since Z1's numerator is going to be 125 minus 65. That's going to be 60 degrees plus I sine of 60 degrees. So there's your answer. And of course, for extra practice, we can convert it. So I'd ask you to pause the video here and convert this complex number in polar form into a complex number in rectangular form. Okay, welcome back. You should have gotten 1 plus I times root 3. You really need to be doing this practice when I ask you to pause the video and do it. You need to try it. And if you get something wrong or you don't know how to do it, that's where when you come to class, you've got to ask me, like, how do you do this? I didn't get that part or whatever. Okay? Now I'm going to have you try one on your own, and I want you to express the answer in both polar and rectangular form this time. So we're going to divide these two numbers. So you try one. Z sub 1 is going to be 10 times cosine of 275 plus I sine of 275. And then Z sub 2 is going to be 5 times cosine of 65 plus I times sine of 65 degrees. All right, so you're going to pause the video here and try and divide these and write it in both polar form and rectangular form. Okay, welcome back. Your answers are 2 cosine 210 plus I sine 210. That's your answer in polar form. And then in rectangular form, that would be negative root 3 minus 1I. So now we can do multiplication and division with complex non-real numbers in polar form. Oh, before I move on, I want to mention that for this division algorithm, we're only really considering angles between 0 and 360. So if any angles are outside of that domain, we're just going to use the coterminal angle that is in this range, or on the interval 0 to 360. What I mean by that, right, is if I gave you if I said like Z sub 1 is 6 times cosine of negative 50 degrees plus I sine of negative 50 degrees. Right? If I give you that angle, we're not using the algorithm with that number. It's got to be, the angle has to be between 0 and 360. So pick the angle that's in between 0 and 360 that's the same angle as negative 50. So instead of negative 50, it would really be 310. So you'd have to use 6 times cosine of 310 plus I sine of 310. All right? You always want to use an angle that's between 0 and 360. Okay, so moving along, we're going to look at now like just what a power of a complex number, a polar, is. It's just kind of an application of multiplying, right? So let's say now we're doing powers of complex numbers. You get the idea that I can write a proof, yeah? So I'm not going to go through a proof for powers. It's a pretty simple one because now that we have multiplication, we know like that we just add the exponents. So let's just kind of do it. Like I'm not going to do an official proof. I'll just do a demonstration. Let's say I want to do z squared for some complex number. And let's say that complex, I'll say z sub 1 squared. Let's say I want to square that complex number. So I'm going to define z sub 1 as r sub 1 times cosine of theta sub 1 plus I sine theta sub 1. Basically, we just do our multiplication formula with it because z squared really means z times z, right? So I do this thing times itself, the magnitude times itself, r sub 1 times r sub 1. But instead of writing that, I can just write it as r sub 1 squared times. Now, if I do cosine, I'm supposed to add the arguments, right, when I multiply. So cosine theta sub 1 plus theta sub 1, since it's the same angle, it's the same number, right, the same angle, I can just say theta sub 1 plus theta sub 1 is really 2 theta sub 1. If I add those together, I get 2 of them. And then plus I sine theta, 2 theta sub 1, again, for the same reason. So squaring, it's actually really easy, right? You square your magnitude and you double your arguments. So then we're going to generalize that to raising it to any power. So if I want to raise a complex number to the nth power, the rule is going to be this. It's going to be r sub 1. I want to do color coded here. R sub 1 to the nth equals r sub 1, I'm sorry, z sub 1 to the nth equals r sub 1 to the nth. So whatever power you're raising to, that's the power of r. We noticed that when we tried to square this that they matched, right? Then times, sorry about that, times cosine, and I'll have, if I did it to like the 5th power, I would add theta sub 1 5 times. So it would be 5 theta sub n, right? So however, excuse me. However many times we're raising it to the power, that's how many times we're going to add theta sub 1. Whoops, I wanted to change the color. So again, you can notice that here that matched that power, right, and that as well. So I'm just color coding our formula for you. Plus I times sine of n theta sub 1. That would be our formula for raising the complex number in polar to a power, okay? And this is where it becomes far superior than rectangular form. This is why we're going through all this. So an example, okay, and this has a name, by the way, the person that developed this, so we'll talk about that in class. But named after the person that developed it. So let's look at an example. So example 3 would be doing root 3 plus I to the 10th. Now we can't apply this theorem on this complex number because it's in rectangular form. And you can imagine that if I had to do this times itself 10 times, even in rectangular form, this would be very tedious and take me probably 20 minutes or something like that. It would take quite a while to do this 10 times itself, because I have to kind of distribute, simplify, then distribute to the next one, simplify. It would take quite a while. So the easier route here is to convert this into polar form. So I'm not going to waste time doing that. I'm not going to do it in the video. You can pause the video and convert this inside number into polar form. Okay, welcome back. So you should have gotten 2 times cosine of 30 degrees plus I sine of 30 degrees. So that's the first thing we would do is if I ever ask you to raise it to a high power, even if it's in rectangular form, you're going to convert it to polar and raise that to the 10th power because of this De Moivre theorem. It's so much easier to do it. So if I want to raise this to the 10th power, we know that we just have to do 2 to the 10th and then times cosine of 10 times 30, because we're going to add 30 together 10 times, right? So it would be 300 plus I sine of 300. It's so much easier to raise a complex number to a high power if it's in polar form. So that's a huge deal here to convert from complex to polar, just so I can raise it to the 10th. And it has other applications as well that we may see if we get into it. So if I do 2 to the 10th, that's what, 1024, and then cosine of 300 degrees plus I sine 300 degrees. That would be your answer in polar. And of course, since the question was posed in rectangular, maybe they want it in rectangular, so you can convert that fairly easily into rectangular form. So I'm going to ask you again to pause the video here and do that. Okay, welcome back. You should have gotten 512 minus 512 I root 3. Okay, so once again, if you're having problems with any of this stuff when I ask you to pause the video, then you're going to ask me about it in class when we're doing the practice. So then this, the powers of complex numbers leads into their inverse, the roots, right? What if I, instead of raising to the 10th power, what if I want to raise to the 1/10 power? Does the same thing still apply? It does. It actually works for, de Morgan's theorem works when n is any real number. Remember, that was our n. So I could take the 10th root of a complex number as well, and that's really helpful in finding roots of equations, solving equations like x cubed equals 1, or I should say x cubed minus 1 equals 0. Find the roots of that equation. De Morgan's theorem gives us a nice way to do that. We are not going to go into that into this video. We're going to just stop here. So you should be able to now multiply, divide, and raise complex numbers in polar forms to any power you like.